Support vector regression is all about balance. Instead of just trying to fit a straight line that minimizes the average error, it introduces a new way of thinking. It says, let's not stress over every little mistake. Let's allow a bit of flexibility, a margin within which small errors don't even count. This is called the Epsilon margin, and it acts like a buffer zone around the ideal prediction line. If a data point falls within this margin, it's considered close enough and we don't need to adjust the model for it. But real-world data is messy and not every point will fall neatly within this buffer. That's where slack variables come in. These act like an allowance for points that are a bit further out but still need to be considered. If a point falls outside the margin, the model won't just ignore it, but it also won't overreact. It will try to adjust just enough to account for those points without compromising the overall simplicity of the model. There is also a trade-off between how strict or lenient the model should be. This is controlled by a regularization parameter called C. A small c allows a wider margin, meaning the model is more forgiving with errors. A large C, on the other hand, forces the model to be more precise, making it try harder to fit every point as accurately as possible, but being too strict can lead to overfitting, where the model starts memorizing noise instead of learning true patterns. The real magic of support vector regression comes from its ability to handle complex relationships in data. Instead of being limited to straight lines, it can use special functions called kernels to transform the data. A linear kernel keeps things simple, treating the data as it is. A polynomial kernel recognizes patterns in how different features interact. The most flexible option is the radial basis function kernel, which allows the model to see nonlinear trends that would otherwise be invisible. At its core, support vector regression is about balance. It doesn't just chase the lowest error like traditional regression. It creates a system where small mistakes are ignored, important patterns are captured, and the right level of flexibility is maintained. The goal is to build a model that generalizes well, meaning it makes solid predictions even when faced with new, unseen data. This careful balance of flexibility, precision, and generalization is what makes support vector regression such a powerful tool. It is not just about finding a mathematical solution, but about understanding how to model real-world data in a way that is both efficient and insightful. Now that we have built this foundation, the next step is to explore how it compares to its cousin, support vector machines, and see where the real differences lie. Support vector machines and support vector regression share the same foundation, but they serve completely different purposes. Imagine you're sorting objects into two categories, maybe apples and oranges. Support vector machines help you draw the perfect boundary between them, making sure that even the trickiest cases are classified correctly. But what if, instead of classifying things, you needed to predict something, like the weight of an apple based on its size? That's where support vector regression comes in. The fundamental difference lies in their output. Support vector machines produce a definite answer, like this is an apple, or this is an orange. The goal is to separate the categories as cleanly as possible by finding the best possible boundary, called a hyperplane. Support vector regression, on the other hand, doesn't classify. It predicts a continuous value. Instead of finding a clear-cut division, it creates a smooth function that estimates the relationship between input and output while ignoring small variations. The way they handle errors is also different. Support vector machines focus on maximizing the gap between categories. They care most about the hardest to classify points, the ones sitting right on the edge of the boundary. Support vector regression, however, introduces the epsilon margin, where small errors are completely ignored. This is what makes it resistant to noise and minor fluctuations in data. Computational complexity also sets them apart. Support vector machines deal with discrete classes, so their optimization problem is often more complex, especially when dealing with multiple categories. Support vector regression, in contrast, can be computationally efficient, particularly when working with large data sets that require fine-tuned predictions instead of strict classifications. Support vector machines are often found in applications like image recognition, text classification, and fraud detection, where a decision must be made between categories. Support vector regression thrives in scenarios where trends and patterns need to be modeled, such as predicting stock prices, forecasting demand, or analyzing customer behavior. In essence, they are two sides of the same coin. One is a powerful tool for making decisions, while the other is built for making predictions. They share the same mathematical backbone, but are designed to tackle very different types of problems. Now